My superpower is engineering. I've been a roboticist almost all my life now. I think engineering is just as creative as the arts. Engineers, we solve problems. It impacts the world. It makes a difference. Without IEEE, I don't think I would have the network that I have. Anyone can get involved with IEEE USA at any time. There's an immense amount of value for anyone at any career stage.
Good afternoon, everyone, and welcome to another IEEE USA Livestream webinar, Semiconductors, an Introduction. I'm your host, Jonathan Cho. IEEE USA's goal is to create programming that is valuable, relevant, and of interest to you. As such, we will be sending a short survey to all registrants after this event, and we would love your feedback. We value your opinions and would appreciate it if you could take a few minutes and share your thoughts. Our presenter for today's webinar is Kathy Herring-Hayashi. Kathy has been involved in the semiconductor industry her entire career, developing, deploying, and analyzing advanced software tools used to create computer and mobile phone chips. At Unisys, she was on the team that created one of the first Sperry mainframes on a chip using custom software. She has since worked for Cadence Design Systems and Centricity, a local startup. She now works at Qualcomm, working with semiconductor workflows in large-scale compute environments. Kathy also currently serves as the IEEE Director of Region 6, is a member of the IEEE Board of Directors, is a senior member of IEEE and IEEE Eta Kappa Nu Honor Society. Without further ado, I will now pass it off to our presenter. Welcome, Kathy. We're very excited for what you have for our audience today.
Thank you, Jonathan. It's great to be here. So today what we're going to be talking about is semiconductors. And what I'm going to be doing is giving a very high-level introduction. So no, we're not going to go into a lot of the deep technical background. We only have an hour, after all. But I do want to hope that you'll understand a little bit more about the semiconductor industry, how the semiconductor chips are made. So let me just talk about the agenda before we get started. So we're going to talk about what is semiconductors. We'll just start with the basics. And then I'm going to give you some high-level overview of making a chip. And I'm hoping to give you just enough information so that you'll understand the basic flow and then want to go down and learn more about the different areas. We're then going to talk a little bit about the ecosystem workforce, the workforce that is making the chips, and some steps that we can do in order to work to keep diversity within technology. And then last, we're going to do a review, and we're going to go over some of the topics. And I hope that after all of these slides, that you'll start to feel a little bit more comfortable with some of the terminology that I'm using, and we'll be able to talk a little bit more about semiconductors. And I hope that you start to get a better understanding of this world of semiconductor technology. So let's get started. One of the first things that we have to understand is, what is a semiconductor? So semiconductor, if you look at the word, that second word is conductor. And it is the ability to conduct electricity. And so you conduct and you insulate electricity. And it is these electrical properties that we're able to harness and able to do quite a bit. Now, when we're making computer chips, there's a lot of different kinds of chips. There could be memory, digital, RF analog, or FPGAs. In the industry that I'm in, I've been worked in digital for quite a while. So hence you see the ones and zeros. But when you are able to harness the power of electricity, you're able to control ones and zeros, control logic, and control transistors. And you can make amazing things happen by being able to use these semiconductor materials. Now, one of the most popular semiconductor materials is silicon. So we'll hear a lot about silicon. So whenever something has those properties, it's called a semiconductor material. Okay. So let's go to the next part. So we understand what semiconductors are. There's something to do with conducting electricity. So then what's the next thing is, what's a chip? So a chip is an integrated circuit. And if you get a bunch of these integrated circuits and you're able to put them on that semiconductor material, and that's what we said in the last slide, it's usually silicon, then we can start making little logic and transistors, and we can start making things happen with the chip. And the more logic, the more transistors, the more components that we put on a chip, the more that it will be able to do. Okay. So as you hear a lot, the semiconductors often refers to the industry of semiconductors, and chips, well, let me show you what a chip really is, and then I'll tell you how it's often used. So the first thing I'm going to do is I'm going to show you a picture. At the very bottom here, you'll see like a printed circuit board. So if you open up the back of a computer, you'll often see that board. And on that board, there's all these different devices. Well, some of those are devices that have computer chips in them. So I'm going to show you a little graphic. Now I found this, it's a short video on LinkedIn, but I'm just going to show you some snippets, and the link is there, but I'm going to show you some of the pictures. Now this is an old package, and if you take the back off the package, and then you can see here they're taking a something to open it up in the back, and they're starting to take the back off, and then underneath that you'll find something in there, and it's almost like finding a pearl. There's a little die underneath that. And underneath that, if you start zooming in, you'll see the integrated circuits. And then after that, you can actually see some of, if you use like electron microscopes, you could actually see the transistors and things underneath it. So this is important for a couple of reasons. So number one, these things on the left is the package. We assemble things into a package. We call it package assembly. And you take this die and you put it in a package. And then you put the package together, and then you can ship a part. Okay. Now, the die itself is, it starts in the bottom, you'll see a circle, and that's usually a semiconductor wafer. And when you have the semiconductor wafer, we'll often repeat the pattern several times. Then we'll take a saw and we'll chop it up until it's a little square, and it's a little silicon chip. And the silicon chip is then what you would put into a package and then serve as a product. Now, the reason why this is important, now this is kind of an old chip, that's okay. But what I want to do is show you the difference between a die and a package. Because right now, there's amazing things that are going on in the packaging world of semiconductors. And they're doing many things. Like here, we've got one die, they're doing stack die, they're doing many different innovations in the package and assembly world. So I want you to understand there is a package and assembly, and they're doing many creative, innovative things. So I hope that you watch out for them and what they're doing in innovation in that space. And then there's also the die. Now the foundries or fabs create the die that go in the package, that go into the part. Okay. So hopefully we know a little bit more about the package, the die, and the circuit. Okay. So now that you know all the pieces, how do we make an overall chip? So let me show you very high level how a chip might be made. So now you already know some of the pieces. Let's put it all together. So it's kind of a trick question when I ask people, it's like, how do we make a chip? And a lot of people say, you start with the transistor, you start with the package, you start with the die. But actually, the truth of the matter is you start with the market demand. You need to find out what you want this chip to do. And you need to find out not only what you want it to do today, but also there takes some time to make chips. So it may be what you're going to be doing in 6 months. It may be do something that, in a year. So you have to understand what the technology is today, and also when you're making the chip itself. So a lot of things are in the market demand. You need to understand the technology. You need to know the marketing of the vertical that you're in. And a lot of these times you will start and create a requirements for what you want to do. So you have basically a requirement stock that will say what you want that chip to do. So you start with looking at the technical landscape and then determining what you're going to make. And then you design the chip. Now, the designing of the chip is on that last slide when you saw all those intricate things through electron microscope. People have to take that idea, that market demand, and whatever you're going to make, try to make the pattern and that the chip is going to have on it. And then once you create that, you create a blueprint, and then you pass that blueprint to a fab, and the fab will manufacture it. So they'll take your design, they will manufacture it, and produce this chip that has your design on it. And then, as we saw in the past picture, it will then put it in a package and assemble it, right? And then after you package and assemble, then it will go into a system integration. So it will go on the board or go into the device, whatever you're trying to put it in, and then you can deliver the product, okay? Very high level. Each one of these represents a significant amount of time, thousands of people, billions of dollars, but this is kind of the way that you can look at it from just a very high level, okay? So figure out what you're going to make, design the chip, manufacture that little piece, put it in a package and assemble it, integrate it with the rest of the system, and then deliver the product, okay? So it is definitely not that easy. So let me show you a picture of what it really looks like. This is a picture from the Accenture, and they may have a really great document called Harnessing the Power of the Semiconductor Value Chain. If you're interested in learning more, please access it. It's a wonderful document. But in this is just showing the global nature of semiconductors and how it goes across the world and accomplishes those things that we just said. So there could be one place where you've decided that you're going to make the chip, but then you may need some external IP, and that's going to be located somewhere else. And they're going to deliver the external IP. Then there's someone else that's going to design the front end of the chip. And then there might be another team that's going to verify the chip itself and then do the physical design. Each one of these can be teams around the world, and there could be thousands of people working on this chip. So then once you have the physical design, then you're going to send it to a fab, which could be in another location, and have them manufacture the chip. Then you take it to another location and have it assembled, put in that package, and then you'll send it someplace else to get tested, and then make sure that the final product is delivered. But to kind of take that from our very simple view, and I understand it's a really simple view, this one is getting closer to showing the global reach and the amount of people that are involved in creating that chip. It's a very complex process, and it is, I hope that you learn more and need to go in each one of these circles and understand each part of this. And what they call this is the global semiconductor value chain. And that is all of the things that are required in order to make a chip. Now, what we're going to do here is I am going to go back to the very simple picture here, but understand there's so much more underneath it. But again, I'm trying to do this in a little over an hour, a little under an hour. And so we talked about the market demand. Let's now delve into the second one. The second one is designing the chip itself. Now, personally, this is where I spent most of my career, is in this chip design. So basically, we were given requirements, and then we're going to create the design. Once we're done, we're going to send something to a fab and have it manufactured. Okay, so that's the piece that we'll look at. Now, there's various types of chips. There's memory chips, there's digital, there's RF, and there's FPGA. And what I'm going to focus on is the digital design flow. However, each one of those others have their own design flow. So let's go into what is a design flow. So we've got the requirements, and now we need to make a computer chip. So how do you even start? So I want to take some of the mystery away from that so that you can at least say you've seen it once on how a chip is made and how a chip is designed. Now, these next couple slides, I had the honor of getting them from Karen Bartleson. And Carol Bartleson was the former president of IEEE several years ago. And she worked at Synopsys, which is a large EDA company. And they're very large and very instrumental in some of the innovations that are occurring in semiconductors. So they write software, and the software that's used. And there are many software companies and even open source software companies that are used in order to create a design. So one of the ways is just give you a workflow of how chips are designed. And this is from Karen's deck. And so these are all the steps that you take to design a chip, and there they are. Now, if I go through each one, it'll take quite a bit of time. But basically, if you look at the top, at the very top, it says specification. Yep, that's the first thing that we get in. And at the very bottom, there's something called a GDS2, which is what we call it's a file. That's the output that is sent to the manufacturer, to the fab, to be manufactured. Okay, so we already know the front and we know the end, but I'm going to just make this even more high level. So what we're going to first do is we're going to do a logical implementation. What does that mean? So you have the requirements, and we're understanding, let's say that they asked us to make a calculator. So the first thing that we're going to do is we're going to write down the logical requirements for a calculator. So let's say that my calculator takes two inputs. So it has two numbers, and it has an output, which would be one number. And so the way that I would describe this calculator is it has two inputs, one output, and its function is to add the two numbers. So given the number 2 and the number 2, I would expect 4 as an output. So there, we've described the logical implementation of a very simple calculator or adder. So once you have the logical definition, then we're going to verify it. And one of the things that I've learned through CAD tools is that we're always verifying. And you're going to see that through the many steps that we go to, we'll make the logical, and then we'll test it. Does 2 and 2 still equal 4? Yes. Okay. And then we'll change it into a different format. Does it still equal 4? Yes. And then we'll change it into physical. 2 and 2 still 4? Yep. Good. And then you put it in the die. We'll check. Still 2 and 2 4? Yep. And then you put it into the package, and then you make the part. And guess what? At the very end, I'm still asking it, is 2 and 2 still 4? So verification happens throughout the design cycle. We, in design houses or engineering design houses where they make this, there's usually large compute grids. And in one study that we showed several years ago, 60% of all the jobs were verification flows. And that was just making sure somewhere along the line that the chip is functioning the way that you would expect it to function. So after you've got the definition and you've transformed it several times, you've verified that it's still doing what you want it to do, then we start translating it into physical. So what that means is that we're starting to do, yes, taking the logic, we're going to make some gates out of it, we're going to make schematics, and then we're going to make physical in the way that the fabs would understand. So fabs tell us, if you want to make a transistor, this is what you have to do. This is what your transistor looks like. And so we put transistors all over the place in the manner that the fab needs it. And that's the physical. There's also several techniques, especially from when this slide deck was made, of DFN. We designed for manufacturing. And what we're trying to do is always make sure that we're making chips that work. Very important. One thing that I can go ahead and mention now is that when we make these chips, one of the things that we're looking for is to make sure that the chips have yield, that make sure that they're working. So let's say that we made 100 chips and 70 of them work and 30 of them don't. It's a complex process. So I'm not really expecting it always to be in the high numbers, because one little dust speck is going to ruin the whole thing. Or if a design rule got too close, it could ruin it. So getting 70 to 100 or 70 out of 100, that is those are good. You like higher numbers, especially in more mature process nodes, but you'll get high numbers. So the yield is 70. It means you're doing quite well. But if you're doing a new process node or something else, you might get fewer yield. You might just get 10 out of 100 working, but that's okay. You got 10. That's great. You can test and you can start doing things, and you can use that to improve the yield as you go along. And if you can improve the yield, or if your numbers are not what you need, you just need to make more. And it could be more expensive, but you could still get the information. Yield is important, because when you ask a fab, is it yielding? Is your design yielding? Those are important things to know. So now you know yield too. All right. So here we've got the different pieces of designing the chip. Let me show you one more picture of how to design the chip, and then we won't go too far past that. Okay. This is just a high level of what each step looks like. So remember, I was showing you that you start with the logical and the physical and then the output. These are not related. I'm just giving you graphical representations of what they are. So the first thing you're going to do is when you're designing a chip, remember I have a spec, and then I'm going to write down what I'm going to do. Then there's several programming languages that are called RTL. And the register transistors, and what they allow you to do is specify. And here you can see inputs and you can see outputs. I'm not sure this is, it says it's a counter, but you've got inputs and you've got outputs. So for mine, I would say input of, A and input of B, and the output would be, C. And then we're going to add them, okay? Now, the only difference between RTL and your traditional computer programming languages is computer programming languages are logical. You go from the top and you go to the bottom, and it's very logical what it will do. In RTL, it's actually time-based. So you're going to go from, you're going to put the 1 down on the input, and then you're going to clock it and go to a register, and it's going to hold, right? And if my 1 got to the right place and my other one got to the right place, then the adder is going to say, yep, 1 and 1, I'm going to output a 2. But if it's too slow and my chip is too slow to get there, then I clock it and my one didn't get there in time. And if it didn't get there in time, then the adder didn't know that I wanted to add that. And then it didn't, it won't get the right values. So clocking and timing is very important. So when you do these designs, it's clock driven. And that's what it's all about, is running it through. We do timing analysis. We do all sorts of things with the timing, because that is the way that these programming languages look at it. Okay. And so if it gets there in time, it's great. If it's slow, it may not have the right results. We got to figure out how to make it faster. And there's techniques for doing that. Or if it got there too fast, hey, maybe I could have done even more. So we could even change the timing on it as well. Okay. So that's what the timing is for RTL. So now we have tools. Okay, now that I've described it, now I start using tools, and the tools that will do behavior to structure synthesis. So we're going to synthesize it. So we're going to use software tools to make gates and transistors. This is actually a pretty bad picture of a gates, but that was all I could find at the moment. So it goes into what ands and ors. Remember that Boolean logic? This is where that all comes into play. So it is able to take this logic and understand that when you said adder, this would be the gates that would be associated with it. And there's a lot of things that we could do to make sure that we get the right gates. We might even have a module called an adder. And then you get the gates. Now, once you do that, and of course we're testing again, making sure everything's ready, then we start going and we run additional tools to now tell us how to get the physical design. Now, these physical designs here, they're actually many different layers, and there's interconnect, which is routing things, and there's modules that are doing some logic. So a lot of times we call this layout and routing. And in layout and routing, it's actually very interesting problems. If you had all the modules and you need to figure out, where do I place them so that they will be optimally routed? So I can actually place things. In fact, there's some games out there today that if you place the circles and you try to route them, if you don't place them in the right places, you can't route between them, right? So layout's important, and then the ability to route in between. And once you have all your modules placed and everything routed, and then we've put them in designs that the fab understands. The fab tells us what the distance between these needs to be, what design rules that we need to follow, and then we run a lot of tests to make sure that all those rules are followed. And again, we test it to make sure that it's still, like if I'm my adder, that 2 and 2 still equals 4. Then when we're done, yet another tool that will output GDS2. Now we have different databases, and there's different database types that we can use. GDS has been here since the days of CalMA, for those who've been in the industry a long time. But it's just right now, they're very large files that have directions for manufacturing, and those are sent to the fab to be created. Okay. Now, technology moves fast. And so some people in the industry, like myself, have actually done all of this at the very early part of our careers, because the designs were small enough and we could actually use tools. And if you're interested in what I did for a career, I wrote the company that I'm with. So it was a large company, and it had its own prototype fabs. And that's the way we used to do it, is that they were large companies, they had their own fabs. We designed our own hardware description language, and I wrote the parsers and the language itself and the parsers that went with the RTL, which are hardware description languages. I wrote behavior to structure synthesis tools to put it into gates. And then I wrote layout tools that actually did that, where you could interactively place your modules. And then I helped debug some of the networking in between it. So back in the day, we could actually do all of this. Today, we have external, the RTL languages are standards across the industry, thanks to Accelera and IEEE. And we have companies, which are called EDA companies, that provide the tools to parse it and do the behavior to structure synthesis, and they do amazing jobs. So we have whole companies doing that. In fact, the group that I was in was acquired by a CAD company, because that's now moving, the things that we were doing in-house were now done in CAD companies. So there's EDA companies, there are CAD software companies, And they would do the translation from synthesis. And then physical design, they would also be doing that. There's companies that are just doing specific areas. And all this testing, there's companies that do the types of testing. And there's a whole thing about putting testing in the circuits itself. So much, much more. But hopefully I've got you thinking about the ways that you can start. There's so much more in each one of these, and I'm not doing it justice by, but I'm hopefully giving you the very high level that hopefully you'll want to know more. What is an RTL? What does it look like? What are the gates? What are the tools used in gates? How do you test? How you design for test? How you design for manufacturing? And what does this GDS file look like, and why is it so big? Okay, so very high level, but I encourage you that it's doable, and if you learn how to do it, it's actually quite fun. Some of these puzzles and the graphics, and I think nothing is prettier than looking at the physical design. In fact, there's whole books on art for physical design. Okay, so that is how a chip is made, so very high level. And here's some more. I just like the diagram because it was looked good, but it was correct in the fact that we do chip specification, functional verification, synthesis, DFT, design for test. That's what we call the front end. So that stuff that we did on the left, that's the front end of the design. And in the back end, we start doing that floor planning. We start working with the clocks, do P&R, place and route, and then you do final verification and output for the GDS2. So hopefully as you see this, at least some of these terms might be a little bit, will pop out a little bit. And when someone says, I do everything from RTL to GDS2, well, look at that. They're doing everything between here and here. So it means when they say they're RTL to GDS, that means they're not the packaging side, they're not the fab side, they're probably not the marketing side, but they're implementation of the chip design. And they've actually told you quite a bit about what they do. So now we know what RTL is and we know what GDS too. And a lot of people that takes different skill sets to do the different things in here. Now, and I got this from, hopefully I've got the links to wherever I got things on the sides. And if not, it's in the references at the back. But there's so much more. And we could go on and on about the entire ecosystems required for chips. But like I said before, in the global systems, we use third-party IPs, we use EDA tools, and there you see written, that's the, the very large companies or open source that is tools used to do all that magic that we just saw. Compute environments, large compute grids are used in order to do all this processing that we're talking about. Hardware security, so important, both hardware security and the IP, hardware security, the IP. Disaster resiliency, making sure that everything is redundant. IP security, again, both in the chip, hardware chip, and the IP itself. And we need project managers, we need data governance, we need documentation. And if you're in automotive or certain verticals, you need additional functionality for like functional safety. So if you're working on automotives, I want to make sure that that chip just doesn't stop in the middle of the road. There's redundancy, there's things that you can do so that you will make sure that the chips will always perform. It may run in a degraded state, but it will run in so that you can get off the road. So there's a lot of functional safety, redundant systems, and extended life cycles. So sometimes if you're making a IoT device, or they have shorter lifespans, and then if you've got a phone, a couple of years lifespan, but for an automotive, it's 15. So when you're designing these things, you have to keep the life cycles in mind. Okay, so much to think about. That's a lot, but hopefully we'll get started. And I hope that you're starting to think about, there are some things that we're going to pick up and some things that will resonate with you, but hopefully you're starting to understand a little bit to demystify what semiconductors is all about. So, market demands are the requirements. Chip design is RTL to GDS2, where we start with something that looks like a programming language. We iterate several times until we get something like a GDS2 to send to the fab. And then from the fab, we will manufacture the part. So before we send it to the fab, I'm going to ask you a couple questions about that chip design that you just created. Okay, and that will determine what we're going to be doing in the fab. So bear with me a second. We're going to lead, if you have your chip and then now you're going to manufacture it, let's review what you just created. Honestly, some of this stuff is happening at the very beginning, before you've even created the chip. But let's just say that you've seen the chip and now that we have it. But a lot of this is determined when you do the market demand. All right. This is a wonderful, wonderful picture of this from, again, the same report from Accenture. I just love it because for those of you in the industry, this is Moore's Law. But this is Moore's Law with a phone in front of it. So first of all, for those who haven't seen Moore's Law, it started like in the 70s. And you always hear, this is the end of Moore's Law. But Moore's Law said that we would double the number of transistors in a circuit every 2 years. And there was actually another caveat on the bottom that said it would also be lower cost. So I didn't see that on there, but that was also another constraint. But let's just talk about the doubling of transistors. Way back when you had transistors, I wish I could have told my future self, that there was going to be an amazing amount of transistors, because at the time when we were asked to double it, we thought that, that's a lot of work. Oh, we're going to have to double it. We're going to have to rerun the whole thing with new design rules. But what it would do is that when you doubled it, you've got the silicon and you've got the chips and transistors in there, right? So they figured out how they can do this through a manufacturing process. So you've got all these chips that are on, all these transistors that are on chips, okay? So at the beginning, we could make enough that was like a phone. It's kind of like my calculator example. I could do an addition, right? This was a phone that could pretty much do phone things. But then if you keep doubling the number of transistors every year, so we're able to shrink it a little bit. We're able to put little design rules in it. And we understand, we can put more transistors in the same area. We can put even more. Look at the number of logic that you're adding each time. So now you're able to do even more with each new chip. So here's a phone that has a little bit more functionality. And then these get, look, it's even got a nice little display starting to come up here. And then look at the phones of today. And that's because we were able to put significant amount of what we're calling transistors or logic, and then it could do more things. And so this is Moore's Law. And in my career, I can safely say that every year we always waited for the manager to show us this picture. And I think every single year we were shown Moore's Law. Now, if Moore's Law flattens off, that doesn't mean that there isn't still innovation. In fact, it's a wonderful time in semiconductors, because what we were measured on before was the number of transistors in a circuit. And our goal every year was to double that number. And that's what we were laser focused as an ecosystem. So it was not only the people that were designing the chip, it was the fabs and the assembly. Everybody was focused on this one goal. And it was amazing because by everybody being focused on the same goal of doubling the number of transistors, look, it was able to do amazing things, right? That is amazing. So, so even though it may have leveled off, there's other innovation going, but the innovation may be in other things that will still allow us to increase the capabilities. You're going to see things like stacked die. You're going to see different packaging. You're going to see many other innovations, but it may not just be number of transistors. So just a side note on that. All right, here we go. So now that we've got your chip and we understand that there's a lot of transistors on it, I'm just going to very briefly, I'm checking the time here, talk to you about power performance area, because that is one of the main things when you're designing a chip. And why is that important? Well, I think so let's talk about these 6 different verticals that are very common when you're making computer chips. So one vertical is communications. So that will be your phone, okay? And the other one are PCs and computers, this laptop that I'm looking at, automotive, car in the garage, consumer goods, industrial, and government. Okay, those are probably your top 6 places that semiconductors will go. Now, in each one of these, one of the main things that we're looking at is power, performance, and area. And you actually know what they are, even though you may not have heard those terms before. So in communications and mobile phones, you want your battery to last. So you care about the power usage of this phone. And so you want the power to be optimized so that I don't have to keep recharging it all the time. Performance, I want to make sure that my games run very efficiently. So you want performance in there. And in area, I want to make sure that it's small enough so it fits in my purse and I get good, it's small enough, right? So you care about power, performance, and area. And on a phone, all of those have to be optimized. And also we care also about cost. That's another parameter you can add in there. For a computer, my laptop, it's hooked up into the power cord here. So it has a little bit more leniency on the power. Performance, I want the same performance or better. And area, yeah, I still want a thin computer, but we got some room here. And then keep thinking along those lines with each one of these. Like for automotive, I got a huge battery in there for power. I do want performance, and in addition, I want functional safety. And area, yeah, I could, there's some places we could put some of these chips and things. So think about that across each vertical. And that's power, performance, and area and cost. And you can look at each one of those. So also what you're going to look at is, why is that important? And why is she bringing that up? Because the power, performance, and area that you're looking for is going to be determining the process node, what process you're going to be using to create the chips. And it also, we want to know how many you want to make. So for phones, we're going to make quite a few because they're replaced every 3 to 5 years. Automotive, I'm not sure how often they're being replaced, but they're a longer time than the phones. So the quantity may be different. And schedule, when do you need it? So there's a lot of different parameters based on your vertical and your power, performance, area needs. Okay, so how does that all come together? Well, this is another, so this one is actually, I want to give credit to, this is from the SIA, Semiconductor Industry Association article as well. They have a really great document, and this is from them. Again, will be in the references. Okay, so let's talk about process nodes. In order to get the PPA that I'm looking for, I need to find the right process nodes. So the process node is the process, the technology that the fabs use to manufacture it. Okay, see, I was leading to fabs. I was going somewhere with this. So here's another this is from the Accenture document that talks about a car. And inside the blue, those are the advanced nodes. So those are the latest and greatest. They're going to be fast. They're looking to optimize PPA. But then also, look, there's other ones that are purple. And so we call those mature nodes. They may have been around for a while, that we've been using them in industry. And so that those processes might be known a little bit more. So depending on what your goals were, will depend on how you want them manufactured. So when you go to a fab, you're going to ask them what process nodes they're going to target, and that will be which chips that they will be manufacturing in their lines. Okay, so if a fab brings up some older, and just so that we can get an idea of what process nodes are, I'm just going to read from here. This one for like the CPU is 6 nanometers and below. Okay, and then if you're going for some of the oil coolant, it's 90 nanometers and above. So that's how we talk about the process nodes. Okay. So we have advanced nodes, which are going to be the latest and greatest. And this one says 60 nanometers and below, and mature nodes, which are 90 nanometers and above. So when you have a fab, you're going to say, are you going to do mature nodes or advanced nodes? And then that'll tell you what kind of chips they're going to manufacture. And oh, by the way, what verticals might be more interested than others. Now, granted, quite a few chips in a car, quite a few chips in a phone. So when the verticals may be looking for a lot of different chips, maybe want to use a lot, different fabs for different chips to go in different areas. But now you know a little bit more about fabs and process nodes. Okay, so the first thing to ask the fab is, what process node are you? And then we can understand where we're going to get this manufactured. All right, so that brings us up to a fab. So if you know what process nodes you are, and so it's not like I can pick the one that's local to me. I need to pick the one that's going to be able to manufacture the part that I need at the cost I need at the schedule that I need, right? So remember those other parameters. So that's where the semiconductor fab comes in. Now, there's some great videos out there on manufacturing. I can safely say there were 0 videos that I saw that were as cool on the design side, but on the fab side, there's quite a few. And I'm just going to let this one run in the background. But if you Google inside the making of an Intel chip, and there are other fabs that talk about how to make a chip. there's really some cool things. This is showing sand becoming silicon, which is one of the substrates for the semiconductors, right? So this is showing it being created, and they're going to take it and then they're going to pull it. And so I'll let you watch that as it goes through. This is about a 7-minute video, so that you can go watch it, and there is some dialogue as well. So they're going to pull this thing up, right? That's the sand going into silicon. And then once they pull it out, then let's see if they get to that part. They're going to start slicing it into wafers, right? And when they slice it into wafers, up at the top left, you see a wafer, right? And those wafers are what we're going to do the semiconductor process on. And on that wafer, we're going to put, you see there's a wafer. We used to use those as mirrors back in the day. You can't do that anymore, but they use the wafer. And then we're going to put that design that the design engineers gave us, and we're going to use masks and lithography and various, we're going to put different coatings on it, and lithography and etching and doping and all sorts of things. You can watch some of these and watch how it's being created, okay? A very delicate process. It can't be disturbed. It can't get, there can't be any motion in the room. There can't be any dust in the room. They're not even handled by humans. They're put in these carriers and sent robotically from one place to another. So it's just a fascinating process. Please understand, this is really fascinating. Creating the designs is cool too, but then when you're making the chip, it's actually a very cool process. So in order to understand this, there are people there that understand device characterization, they understand physics, we understand how things work together. Lithography was a big thing. I used to tell people that, how do you make a chip? And I used to say, well, it's like when you're making a photograph and you're putting it in different chemicals and the photograph pops up. But most people don't know that anymore. So that's not a good example anymore. But you make a mask, you shoot light through it, you put, and use it as a template to go. So I don't want to, I have a very simplistic view of it, but please watch the videos, and there's a lot of discussion, and this is a whole industry, amazing. And that is the thing with semiconductors. It's just amazing how this all works and comes together. So someone started with a document about what we wanted to make, and then we had whole design teams that actually designed it. And these out of this world manufacturing places are making it, right? So that is why the semiconductor industry is so interesting to me, because I will always, whenever I get a new phone, and especially if it might have been a phone that I was at all involved in, when you turn it on the first time and it works, and then I bring up my favorite game works, and just to think about all the things that went into bringing it to you, and it works. And that's because throughout this whole cycle, there's I like to say magic, but it's not magic. It's very designed that we design it, we check it, design it, check it, and then amazing manufacturing fabs like these that are able to take those designs and then to make it. So when you actually get these, you get a device and turn it on, just think about all the things that happened in order to make it happen. But what you've seen now is the basic process for making that happen. So please watch the rest of this rest of this video. It does have audio on it, so when you go to watch that, there's another good one here that flips through it. It goes through basically these steps and processes here, and this is from the documents that I'll reference in a little bit. But there's your wafer, and then you slice the die, and then you then go back to that first slide where we put it in a package and assembly. But believe me, there's testing all along the way. So there you have it. That is how a chip is made, and I hope that you have taken away some of the little mystery, but still leave you in a little bit of awe of how this is made, because now I hope that you're asking a lot of questions and you want to know more. So hopefully I'll give you enough resources to get started. So to continue on, some of the things that we also want to talk about is the workforce. And so from this, I hope you see that this ecosystem is huge. And it's depending on where in this process that you want to dive in. But when I was talking about the very front, we need marketing people, technical analysts, engineering technologists who look at the future, right? Just in that box alone. And then the other one where we're designing chips, we need people that understand, that are very good at logic and statistics. In fact, I had a logic class, and that was one of my favorite classes, and probably the one that I think came in the most useful here is because you have so many logic problems, and they are problems that you work to solve, and they're a lot of fun. So people that are designing the chips, people are verifying the chips, people that know physics, people that know how the physics of the transistors being created. But we also need people that understand the compute environment, because this takes an enormous amount of compute, and it has to be optimized for the semiconductor industry, because we can't just use any computer. We need to use computers that are optimized, that have the storage that fits the designs that we're trying to do. The displays, many of the displays that we're using came out of the gaming industry, because we were looking for the displays that were fast and had low latency and can be used across globally, right? So the displays that when you're looking at a chip and you're zooming in, and we need amazing displays. So I hope that you see that throughout the ecosystem there is a need for so many different types of people and skills. And I hope that as we start looking at the workforce, that we'll be looking at a lot of those. So one of the questions that we have is, as we're looking at the workforce for the ecosystem, let's make sure that we are looking for the diversity in everything that we do. And there's several strategies that many large companies have done that are very successful, and I applaud each and every one of them, and they are thankful. So some of the things that they're doing to support a diverse workforce. And so some things, I'm going to name just a few of them, but there's a list. In fact, if you look at the CHIPS Act documents, they even describe, even in more detail, some of the things that for diversity that we have in many large corporations, but hopefully we can get to many more areas as well. The first one is near and dear to my heart. It's called returnship programs. And returnship programs are for those that need to leave the industry for whatever reason. So if you need to raise a child or take care of elders, or you're going to the military, or for whatever your reason is that you need to leave the industry, but welcome them back. Welcome them back after 1 year, welcome them back after 10 years, welcome them back after 18. So the returnship programs are those that want to re-enter the industry. Now, you still have to apply for the job, and usually they're internship positions, but generally paid internship positions. And you will get a mentor. And the mentor will look at where you left the industry, what it looks like now, and hope to fill you in on the gaps so that you can be productive and engaged in the technology as it is today. So, for example, one reinternship program is that person came back and they said, well, where's Skype? It's like, oh, we don't use Skype, we use Teams. So found out how to use Teams. What process node they left with, and what process node that we're working on now. And here's the differences. Here's the tools that we use, and here's the way. So they understand the basics of the whole semiconductor industry, but returnship programs allow you to come back. So applaud that. Many companies have returnship programs, and they're very good for diversity. And I hope that we spread the word on returnship programs so that people feel okay about leaving and coming back. Diversity networks inside your company, having networks and groups for people so that they can talk amongst themselves and support each other, and also allyships, getting people together to understand how to be good allies, what are techniques for allies, and how they can help, and also working with people and their transferable skills. And you're going to see that in also as we grow this industry and how we can use transferable skills. So you may be good at statistics with baseball, but if you understand that and can make box plots, and you can make diagrams and know artificial intelligence with baseball data, okay, let's change some of those into semiconductor wafer, lot, die, and yield, and then we'll show you what the semiconductor industry does with the same sort of data. Okay, so they're transferable skills. We just need to apply them to the semiconductor industry. In fact, that is actually a true story. That is how we got Java programmers to work on yield design, is by understanding what they were interested in, giving them data, making sure that we got the graphics and analytics that we need, and then we brought in the semiconductors from the and the yield data as well. So transferable skills. Also using for diversity, equity, and inclusion, making sure that we hold ourselves accountable, that we're looking at the metrics and doing everything that we can to try to improve the diversity in all diverse categories. So when we talk about DEI, there are many categories, and I hope that we focus in on at least some of them so that we can bring them all up and use your metrics in order to guide, get baseline metrics and then goals. Also providing opportunities. I think that is one of the things that everyone's looking for, is not just only the support and the encouragement, but also the opportunities. So if there's opportunities to be on industry advisory councils, if there's opportunities to learn new skills, if there's opportunities to even present today, and thank you IEEE USA for allowing me to present, having those opportunities helps. And it helps us to expand our skills and to maybe even work to get into other verticals. And if you saw from my career, I went across the stack in semiconductor design. And each one of those, someone gave me an opportunity to work in a different area. And when I was done, I had done almost every single area in the digital design space. And then the last one is professional development. I strongly encourage that for professional development, please try not to, those people that are in the diverse areas certainly will benefit from classes, but try also to give classes to everyone so that they understand what diversity looks like, how to hire people that don't necessarily look or act like yourself, how to write job requirements so that they're inclusive, and providing professional development, focusing on how we can all work together to create a more inclusive environment in semiconductors. So I will just stop with just a few more on diversity and just show you a little bit about the state. Again, these are things that are working by large companies, which I am so thankful for, and I applaud everything that they do, and any ways that I can support them, I certainly would like to do that. The reason why that I'm doing that is because of some of the statistics. Now, in terms of diversity, one example is sustaining women technology. Prior to the pandemic, the data that we all know in the industry and have seen before is that women do not continue in the industry, they drop off. And there's all sorts of statistics and all sorts of numbers. We need to make sure that we have the current numbers. They're pre-pandemic numbers. Some things like 1/3 leave within their first year. Many leave 10 to 15 years in, 2/3 quit after 15. We need to figure out how to sustain diverse groups in technology. We can bring them in, but we have to keep them, and we have to keep them and sustain them. So this is from the Center for Creative Leadership. They give many good presentations in the past. They have a lot of data as well. They gave their focus is to challenge, connect, and invest women. So they're giving active strategies on how to retain women in technology. But this is a statistic that we need to keep watching and keep seeing if we can keep making sure that women or other diverse areas stay in the industry. So when I look at what can we do for diversity, is find ways to sustain them in the industry, make this environment that they would stay. And as always with any of these, please look at the metrics. This is the data from 2022. The dark green bars are the women in technology, and that's just all women. Great statistic, but then also look at the other bar, which many of the diversity reports have. They're very open about it. Is the ones in the lower ones here are those that are in technical roles. So when you're bringing the STEM in there, these are the green bars that are technical roles. But in looking at all these, we are like 1% increasing. So we're struggling to increase, but we're consistent and we're really trying. But hopefully, can we find ways that might help move that needle a little wider, a little faster? What are the things that we can do? And from the other slide, sustaining women in technology, what are some strategies from that? And the previous slide talked about some of the things that some companies are doing with success, but we need to continue to do exit surveys and surveys for and actions for what we can do. And again, let the metrics guide you. The one on the right is about the pandemic. I led several women in engineering conferences during the pandemic, and I can only say that it was very difficult for large groups of women around the world as the pandemic hit, and having to focus on, they couldn't focus on their careers. They needed to focus on other things, which were more important, absolutely. But they needed to leave the industry for various reasons. And now, as many are being asked to come back into the industry, it's difficult, and the women are coming back a little bit slower than some of the other demographics. So let the metrics guide, and let's see how we can help. Now, these are diversities in, again, it's women in technology, but there is diversity metrics for many of the other diversity areas, and I want hopefully to have focus on many of those areas. This one on the left was from Deloitte, and I have the links and references for that as well. Okay, so many strategies. The strategies are within, once you're in the industry, retaining them and creating healthy environments. And so those are the diversity things that within the industry that we are working on, and could certainly use additional help as people are working on these various initiatives. Okay, I just have a few minutes left. So hopefully through all this, what I wanted to do is to kind of break it down so that you could see, just get a little insight into how semiconductor chips are made. Take a little bit of the mystery so that at least we can start talking. And I need us all to start talking about semiconductors, how they're made, innovations, and working with the other areas, working with the STEM groups, working with the universities, working with the new technologies, the labs to fabs, all these. But we can't start talking unless we get more comfortable about talking with it. Now, hopefully this is one tiny step forward in doing that. So through these, I always loved Friday when we did the vocabulary, and you had to use everything in a sentence. So I'm going to very quickly use some of the terms that we've learned, and we'll use them in sentences so that we can try to understand what it is. So RTL GDS2, when someone says, I spent my career in RTL GDS2, or I'm conducting a class on RTL to GDS2, we know that that's someone who's working on the design on the chips, right? Pre-silicon is something that goes before the silicon. So it's before you toss it to the fab. Now, pre-silicon often refers to pre-silicon verification versus post-silicon verification, but in general terms, pre-silicon is something that happens before we toss it to the fab. So it's that digital design part. Fabs versus foundries, there is a difference. Fabs are places that manufacture semiconductors. Foundries have a fab and are offering the service of fabs to other people. They're in the business of fabs. I read an article that was trying to explain there's fabs, there's fabless, there's foundries, and there's all different combinations of two on whether your company owns a fab, doesn't own a fab, owns it and has a fab. So there's all sorts of things, but just know that foundries are, they have fabs as a business, and fabs are what manufactures it. Process nodes, you've learned all about process nodes. There's advanced process nodes, there are mature foundry nodes. And when we get a fab up and running, I want to ask two questions. What process nodes are you targeting, and has the fab started yielding yet? And usually when you start yielding, to go on to the next one, a fab will work with someone who has the design, right? Because they need the designs. So they'll work with someone that has the design in order to work with them in order to bring up the fab. So they'll run a design through, look at the yield, change some knobs and changes, and the designer might change some things, and then they'll keep working together until they can get that fab yielding. So there's a lot of industry collaborations, and we're not hearing a lot about the design centers or the industry collaborations. And I'm hoping as the CHIPS Acts continue that we will hear more about what those relationships are going to be. We also learned packages versus die. So you understand that there's that component, there's a package and assembly, and then there's the die that goes in. Amazing things going on in the packages. They are on fire with the innovations and the number of conferences that they're having. They're talking about stack die, how they're going to do interconnect. So watch the space for packages, but understand that packages is a different box than the foundries and different box than the design. All interrelated. It's all one wonderful ecosystem, but there's different areas. Sustaining women in technology diversity is going to depend on being able to sustain diversity. And one metric to look at is how we sustain women in technology. If we get them all the way here and they leave within 3 years, that's not what we want. And if we get them here and they leave out of the industry, middle, of the careers, that's not what we want. So help find ways to keep them in, to keep them in here. I would be happy to discuss with anybody about some of the previous conversations and some resources. Certainly we could talk a lot about how some things that we could do in that area. And last, supporting diversity networks, diversity, equity, inclusion, using metrics and setting specific goals. So I hope you've learned a lot about semiconductors, but wait. Okay, here, I'll just very quickly. Here, there's more. IEEE USA has some amazing events coming up, and this is just the first of many. IEEE USA has, this one is the first one. Hopefully I've raised a lot of questions and you can use a lot of these. On July 12th, there's going to be another conversation with Matt Francis and David Bondurant on the CHIPS Act. And so hopefully you can ask them some of the questions that you heard here today. What process node are they using, or what process node did you start with? Did you do design from front to back, and things like that? So enjoy that conversation. I know it's going to be really good. I've read the bios on both, and it should be a great conversation. I know I'll be attending. And then there's also the monthly updates. Aline is giving updates, and part of those are on the CHIPS Act. The CHIPS Act activity is moving so fast. It's good to stay current, because then I was looking at something and it's like, yeah, I don't know, if that's passed or not. And she gives you the latest updates. So stick around for those. And then also there's a conference in Arkansas talking about a very specific part related to the CHIPS Act on innovation, workforce, and research. That looks amazing. And in San Diego, we will be talking about the fabless, or the design center, the pre-silicon part, and how it relates to the whole ecosystem on chips. There's some additional resources, and hopefully you can go back and screenshot that for some of them. Great reads. If you're interested in the semiconductor field, it puts these in things that you can really understand. Specifically, the Accenture report is explained so well in terms that are hopefully many can understand. And the Semiconductor BCG report on strengthening the global semiconductor supply chain, just an awesome read as well. And so please check out these. And I think these are really good for those that are new to the industry and give you good and accurate information. Thank you very much. My email is kathy.h@IEEE. Please email me if you have any questions. I hope that you can see that this is a wonderful industry to be a part of. And I certainly have been glad to be a part of this industry for so long. So thank you, everybody.
Fantastic. Thank you so much, Kathy. Folks, so unfortunately we are out of time. We went over a lot of information. We went over a lot of information. And again, if you have any questions, be sure to reach out to Kathy. And we have, as she also mentioned, we have plenty of more materials and webinars coming up. I would like to mention Aline's DC legislative update is bi-weekly, actually. So our next one is on July 6th. The following one will be on July 20th. So we will be sending those links out to you. Kathy, thank you so much for joining us today and for providing our audience insight on the process of semiconductor chips and just everything related to. I'm sure our audience got a lot out of it. So thank you so much.
Thank you, Jonathan. It's great to be here. And thank you, IEEE USA, for having me.
And thank you to our audience members for tuning in. If you found this webinar topic interesting, be sure to register for our other upcoming webinar, the CHIPS Act, a new era in the U.S. semiconductor. Let me just pull that up real quick. Being held on July 12th at 2 p.m., sponsored by IEEE USA in the Center of Excellence for Wireless and Information Technology at Stony Brook, and presented by IEEE members David Bondurant and Dr. Matt Francis. It'll be very, very interesting. As the CHIPS Act is something that IEEE USA has been working and a big proponent for the last several years. We will be highlighting the details of the CHIPS Act passed last year, including how it returns leading edge manufacturing to the U.S., reinforces our traditional strengths in chip design, and more. So we've included the links below. 1 second. Please don't forget to like, share, and subscribe to our channels on social media, and check back daily for future live stream updates. Thank you so much, everyone.